Hello everyone, and thanks for joining us for the Advances in Battery Research 2024. My name is George Hammond, and I'm here to moderate today's event alongside my colleagues Princess Sennett and Heather James. Before we start the talks today, I just have some general information and a few tips for getting the most out of the event. We would like to ask if you could please refrain from video, audio, or photo recording of all talks. Many of our speakers have kindly agreed to share their slides with you, and these are available within the literature section on the platform. Please remember that we encourage debate and discussion and welcome all of you to use our networking services to introduce yourselves to other attendees, but we do not permit the overt solicitation of products or services and reserve the right to block any user who infringes on this rule. It's also incredibly important to say that this event was only made possible thanks to the generosity of our sponsors and partners, particularly our platinum sponsor, Agilent. For more detailed instructions on how to make the most of the features available to you at the event, please navigate to the event home and watch the overview video at the top of the page or visit the FAQ section in the left-hand menu. With that out of the way, I will now move on to presenting our opening session for the event.
Thank you. It is my great pleasure to introduce our keynote speaker, Professor Wei Lu, presenting a talk on transforming battery design with simulation and machine learning. Professor Wei Lu is a full professor at the Department of Mechanical Engineering at the University of Michigan, Ann Arbor, and the director of the Research Center for Advanced Battery Coalition for Drivetrains. He received his bachelor's degree from Tsinghua University and a PhD from Princeton University. Professor Lu uses multi-scale and multi-physics modeling and experimental approaches to address challenges in energy. He has more than 180 journal publications in high-impact peer-reviewed journals and over 200 presentations and invited talks in international conferences, universities, and national labs, including Harvard, MIT, and Stanford. A warm welcome to you, Professor Lu. Following the presentation, we will have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. And without further ado, I will now hand over to Professor Lu to begin his presentation.
Thanks for the invitation and introduction. It's a pleasure to give this keynote speech. We know that lithium-ion batteries have many applications, from consumer electronics such as cell phones and laptops to electric vehicles and grid storage. Current battery technologies need substantial improvements in capacity, cost, and lifetime to meet the industry needs. Our mission is to create validated battery material, cell, and pack models to speed their insertion into advanced electrified drivetrains and to educate successive generations of industrial and academic workers to enable continued innovations in the field. To support the mission, we have established a comprehensive in situ and ex situ material and cell categorization and testing facility. This allows the fabrication of cone cells, pouch cells, specialized cells, measurement of the complete set of cell electrode and electrolyte parameters, categorization and testing of batteries and various environmental conditions, and in situ studies of the solid electrolyte interface, dissolution, and fracture. Our research areas include three parts: multi-scale, multi-physics modeling and simulation, material categorization, cell fabrication and testing, and smart battery management system and control. We emphasize on battery degradation, optimization, and control. First, let's look at how a lithium battery cell works. A battery cell is composed of anode, cathode, and a separator. They are soaked in the electrolyte. During discharging, lithium ions flow from the negative electrode or anode to the positive electrode or cathode. Outside of the battery cell, electrons flow in the same direction and do work, such as drive an electric vehicle. During charging, the process is reversed. Lithium ions move back from the cathode to the anode. However, the process is not fully reversible. Various side reactions can occur. This causes the cell capacity to decrease with charge-discharge cycling. For instance, the formation of solid electrolyte interface, or SEI, consumes sectable lithium. Fractures in the anode and cathode cause increase of resistance and isolation of active material. Dissolution leads to the loss of active material. Lithium plating causes lithium deposit on the anode surface rather than integration into the anode for storage. These complicated processes and their interactions lead to capacity degradation. Therefore, cell degradation is a complicated, multi-scale, and multi-physics problem. Understanding cell degradation is critical to design better batteries, increase the battery performance and the lifetime, and develop advanced control strategy to prolong the battery life. Physics-based model can be used to optimize battery design and manufacturing to deliver better batteries, such as electrode thickness, new architecture, and health optimization. The model can also be used to optimize the use of batteries by control through the battery management system to ensure battery safety and long cycle life. I will focus on 4 topics: how to couple mechanics and electrochemistry, the development of a comprehensive degradation model and life optimization, the use of machine learning for battery design, and a new strategy to stop dendrite formation. First, let's look at the coupling of mechanics and electrochemistry. A porous battery electrode is composed of many small active material particles bonded together. With increasing demand of specific energy and energy density, more lithium is integrated into the high energy electrode material. This causes increasing volume expansion of the electrode after lithium integration. The associated stress can lead to various failure in the electrode, such as fracture in the active material particles. The behavior of fracture inside a single particle is known. The strain includes a mechanical strain part and a strain associated with the volume of lithium ions. Here, C is lithium ion concentration in the particle, and omega is the partial molar volume of lithium ions. This latter part is similar to thermal strain. Studies have shown that smaller particle size leads to more uniform concentration distribution. Smaller concentration gradient leads to smaller stress. This figure shows that for a given charge-discharge current density, when the particle radius is small enough, no fracture occurs. However, experimental observations show that electrode level crack and fracture can occur and have a major impact, especially for high energy materials. For instance, black phosphorus is a promising anode material with a high energy density. We can observe significant electrode level cracks in the electrode. different from the cracks in a particle. Electrode-level cracks are between particles. Degradation caused by cracks in between particles is a major problem. Understanding continuum electroscale behavior needs coupling mechanics and electrochemistry consistently at multiple scales, with consideration of the effect of mechanical stress on electrochemical reaction and consideration of particle interaction. Now let's look at how mechanics affect electrochemistry. First, stress changes the chemical potential of lithium ions. In addition to the regular chemical potential μc, there is the additional term. Second, stress changes the overall potential for chemical reaction. At the microscale, stress affects lithium-ion diffusion in the solid particle through μ. During integration, lithium is under compression closer to the surface and is under tension close to the center. The stress gradient on sigma H promotes lithium diffusion into the particle. At the continuum scale, stress affects the integration current distribution. Imagine two particles, one under smaller compression and one under larger compression. The difference in overpotential associated with stress causes more lithium-ion flux toward the particle under a smaller compression. In addition, the large stress can squeeze lithium ions out of the particle and integrate into this particle under a smaller compression. Therefore, mechanical stress can significantly affect lithium-ion flux at electrode level. We developed a multi-scale model that accounts for the interparticle interaction and effect of external stress. To demonstrate the application of this multi-scale model, we consider a half cell with a cathode, a separator, and a lithium metal anode. The x direction along the electrode thickness direction. The y-axis is along the in-plane direction of the electrode. This shows the concentration distribution inside a particle. The horizontal axis shows where the particle is along the x direction. The vertical axis shows the position inside the particle along the radial direction. The model allows us to calculate the stress due to concentration inside the particle and the macroscopic stress. Here, the horizontal axis is the x direction and the vertical axis is the y direction. We can further apply the obtained macroscopic stress at any location inside the electrode on a represented volume element to recover the detailed particle level stress, including stress concentration. Note that each represented volume element is composed of many particles representing the particle distribution. The developed body-scale model allows us to analyze various electrode level behaviors such as electrode level cracks. Here we show an interesting degradation mode that we found using the model. Some small local regions in a composite electrode may lose their activity due to disruption of the electronic network, local dry-off of the electrolyte, or blocking of the particle surface. We call this electrochemically inactive regions. Here we put an inactive region in the model. The inactive region is similar as other region mechanically, only that the material in the inactive region does not participate in the electrochemical reaction. It is not a crack, so it has not received much attention before. We find that the inactive region can generate stress concentration. The large macroscopic stress can cause debonding between particles, leading to further growth. This suggests that such hidden damage can be important for battery applications. Here is an example of using multi-scale approaches to analyze the delamination of active particles from the binder. Using molecular dynamic simulations, we obtained the traction separation curve. We then identified key parameters, such as the maximum traction and cohesive energy, and input them for cohesive zone elements to model delamination. Here we see the lithium-ion concentration distribution. Because the flux of lithium ions is blocked by the binder region, the concentration distribution is not spherical symmetric. With increased state of charge, more areas are debonded. The debonded areas are shown in the red color. Interestingly, we find that interface debonding is more likely to happen at a smaller particle size and a lower C rate, which is opposite to the case of fracture inside a particle. So we have a window of particle size, not too large to avoid crack in the particle, and not too small to avoid delamination from the binder. When crack occurs in a particle, lithium will be trapped and cannot participate in integration deintegration. For instance, here we can observe a large difference of lithium concentration on the two sides of the crack. This reduces the usable capacity. Using active material particles with a core shell structure is an effective strategy to combine the advantages of two materials. However, two failure modes can happen to cause the structure lose its integrity. This includes delamination of the shell from the core and fracture of the shell. The core-shell interface is prone to debonding for particles with a thick shell, while shell fracture is more likely to occur for particles with a large core and a relatively thin shell. Coupled mechanical electrochemical analysis allows us to generate a design map to avoid both failure mode. Now I introduce the topic of comprehensive degradation model and life optimization. As we mentioned before, various side reactions can occur in a battery cell, causing capacity degradation. We integrated SEI growth, lithium plating, manganese deposition on the anode, and solvent oxidation, salt decomposition, active material dissolution on the cathode side, and processes such as fractures. By considering the transport and the balance of species and charges, we obtain a comprehensive degradation model. Over the years, we have enriched and validated the model piece by piece. In the following, I show some examples of understanding and application of this model. The model revealed that degradation has three stages: the acceleration stage, stabilization stage, and saturation stage. SEI growth consumes a lot of secretable lithium and causes the acceleration stage. As the SEI layer grows thicker, the SEI formation on the anode surface slows down, and the battery enters the stabilization stage. In the saturation stage, solution-induced active material loss, particle structure distortion, and particle isolation develop further, leading to further capacity decrease. Associated with capacity degradation, The state of charge swing window of the cathode and anode show unique patterns. This can be used to identify the state of health. Traditionally, battery optimization is only performed for specific energy and specific power. The lack of a reliable battery degradation model has precluded battery health optimization. With the developed comprehensive battery degradation model, we can now optimize battery design to achieve a better battery with longer cycle life. We first perform a specific energy optimization to achieve the maximum possible specific energy. We then set a specific energy requirement slightly lower than the maximum so that there is some room to make parameter adjustment. We further set a power density requirement and then conduct battery health optimization. After optimization, battery degradation is reduced from 60% to 20% after 100 cycles. This is 3 times increase of battery life. However, the specific energy is only reduced from the maximum slightly. So, a slight sacrifice in specific energy yields a significant improvement in battery health. The balanced health and specific energy design can help to significantly reduce the reserve capacity and thereby reduce the battery cost and weight. Parameters involved in battery design include everything from the materials used to the thickness of the electrodes to the size of the particles in the electrode and more. Testing each configuration usually means several months of fully charging and then fully discharging or cycling the battery 1,000 times to mimic its use. It is extremely time-consuming to repeat this test through the huge number of possible battery designs to discover the better ones. We developed an approach that could cut the time for both simulation and physical testing of new and better batteries by about 75%. Here, the key challenge is that evaluating objective functions such as the battery capacity after 1,000 cycles is very expensive. So our innovation is to leverage the intermediate data, and many batteries do not need to cycle to 1,000 cycles for us to find the better designs. Here is our approach. We cycle multiple batteries with different configurations at the same time and use a pruner to periodically remove the low-performance batteries from the cycling channels. Here, cycling can be either physical testing of batteries or by simulations. Notice that even simulating 1,000 cycles can take a long time. The saved channels will be used to test new battery configurations. Many testing battery configurations will only be cycled shortly, such as 10 cycles or maybe 100 cycles. So the testing time is greatly reduced while we can explore and compare various battery configurations using the saved channels to look at new configurations. The idea may seem simple. However, simply discarding the low-performance batteries in the early cycling stages may cause issues because some of them may actually perform better in later stage. So we developed this systematic strategy to keep some selected low-performance batteries to continue cycling for a certain time so that we do not miss the battery configurations that will be better in later performance. Furthermore, we use a sampler to determine new Curie points based on existing observations. since the objective function, which is the battery cycle life after 1,000 cycles, is very expensive to evaluate. So we need to automatically determine the most promising new trial battery parameters for cycling based on historical data. So our key idea is to leverage all those middle data, those battery data that has stopped before they reach 1,000 cycles, and then many of them stop very early. So we can leverage this data and use our sampler to output the configuration that is most likely to be the best one. This is achieved by a Gaussian mixture model. This is an example using simulated data, which demonstrates that the approach can quickly determine the optimum battery parameters. The next topic I'm going to talk about is machine learning for battery design. Simulation-based battery design encounters the difficulty of a high computational cost. We developed a systematic approach based on the artificial neural network to reduce the computational burden of battery design by several orders of magnitude. This is not as simple as just training a machine learning algorithm with data. The figure on the left shows finite element simulations of specific energy and specific power for various combination of parameters. We can observe that some results seem to show a trend, such as the lines, while some others seem to be random, giving very small specific energy. Upon further investigation, we found that these low specific energy values are due to electrolyte dry out. In other words, for the given design parameters, the battery cell cannot sustain the required C rate. We consider this as abnormal cases. The abnormal cases will pollute the training data. If you use all the data to simply train a neural network, it will not converge. To address this problem, we built two networks. The first one is neural network as classifier. It will be trained with both normal and abnormal cases and then learn to classify the two cases. The second one is neural network as calculator. This network will only be trained with normal cases identified by the previous classifier neural network. For demonstration, we choose 6 inputs, include electrode thickness, volume fraction, Bruggemann constant, particle radius, electrolyte concentration, and the C rate. The output is specific energy and specific power. The figure on the left shows that the plot from the neural network agree well with the finite element calculations. Meanwhile, the computational cost is greatly reduced. Note that the input variables for this validation are out of the training dataset. Each dot in the figure takes about 6 minutes of calculation. Thus, finite element simulation can only be performed at several discrete series due to the computational cost. The dots in the figure take a total of 3 hours of computation. In contrast, it takes less than 1 second for the calculator neural network to generate the entire continuous curve. The figure on the right shows the sensitivity analysis of the input variables on specific energy and specific power. The electrode thickness and porosity are the dominant factors affecting specific energy. By contrast, the applied current density is the decisive factor on specific power. This figure shows the design map for the two most sensitive parameters, electrode thickness and volume fraction of solid. Thick electrode and a high volume fraction of active materials lead to high specific energy but low specific power. The contours can be combined to fulfill both requirements of specific energy and specific power. The green area denotes the feasible region where the specific energy is larger than 160 and the specific power is larger than 300. we further applied machine learning approach for design of battery channels. To increase the specific energy, using thick electrode can help. However, with thick electrode, the diffusion of lithium ions will be reduced because it has to diffuse through a larger thickness. To facilitate lithium ion diffusion, motivated by what we observe in nature, such as trees, which deliver neutrons efficiently, we can create channels in the electrode so that the lithium ions can move quicker through the channel and integrate the electrode. Here we designed this neural network with input parameters such as the channel length, width, taper angle, and so on. And the output is specific energy, specific power, and specific capacity. So we use finite element calculations to generate training data and train the neural network. With that, we can use the neural network to design better batteries. This allows to design optimized channels in the electrode to facilitate the diffusion of lithium ions in the electrolyte, therefore increase the performance of the battery. A major challenge with the physics-based model is the battery parameters. There are a lot of battery parameters and they depend on temperature, state of charge, or other state variables. Getting these parameters are complex and expensive. We developed an approach by embedding physics law and online observation into machine learning so that irrelevant low-cost battery data can be utilized to identify complex system parameters by machine learning without knowledge of their ground truth as training data. For instance, lithium diffusivity is a crucial parameter for battery performance, but it's difficult to measure directly. Lithium diffusivity D is a function of concentration C. Here, the challenge is that we have no data on D or C, so that we do not have a training dataset to train a typical machine learning model. Our approach is to embed the battery physics into machine learning through regularization. Then we can use the low-cost, easy-to-measure battery voltage and current data to obtain lithium diffusivity. Here are some examples. We can show that using this approach, we can estimate the battery diffusivity even if it is a function of concentration C. For the figure on the right, we can observe that even when we have a very complex dependence of diffusivity on concentration so that it is not one-to-one mapping. For instance, for different concentration, we can get the same diffusivity. Even for such complicated cases, the approach can correctly estimate the battery parameter. We also added noises to the data and showed the robustness of the approach against noise. Next, I will talk about self-directed online machine learning. This is an effective approach that we developed to optimize material distribution. In many designs, we need to distribute the materials. For instance, for battery application, if we want to optimize the shape of the battery electrode, we need to distribute the solid material at different physical space so that we can create the desired shape. This is a common problem because of the high degree of freedom. Take the figure on the left as one example. Suppose we want to build a tower with 1008 bars, and each bar has 16 diameter choice. If you look at all the combination, the design space is 16 to the power of 1008, which is roughly 10 to the power of 1214. That's huge. So we need an effective approach to accelerate the optimization so that we can get the optimized geometry. The approach we developed is called self-directed online optimization, which is called SOLO. The idea is the following. We dynamically train a DNA network, and this will learn roughly the landscape of the objective function. Then only in the region of interest, we dynamically generate the data and train the machine learning to learn well in this local region. And if you look at the figure on the left, we can find that even if the value is different between the neural network prediction and the true value, well, the position of the optimized point are very close to each other. And because we don't need to learn the entire function, we only need to learn the function locally at the region of interest. With this, we can dramatically accelerate the optimization. Here are some examples to demonstrate the power of this approach. We have found that it outperformed all state-of-the-art approaches, and it accelerates the calculation by up to 5 orders of magnitude. So this allows us to solve many problems not possible before. For instance, we can use this approach to optimize the shape of the electrode to improve the battery performance. Now is the last topic, a new strategy to stop dendrite formation. Dendrite is a major barrier for lithium metal batteries. This video shows the dendrite growth. You can observe the dendrite grows and push the separator. When the dendrite penetrates the separator and bridges the anode and cathode, internal short circuit happens. This can lead to fire or even explosion. Dendrite also leads to low Coulombic efficiency. We developed a model for concurrent dendrite growth and SEI growth on top of it. So first, I will introduce the concept of SEI coverage density, H, as a function of X along the material surface. It's defined as the volume of SEI on a unit area of the substrate surface. SEI coverage can be understood as the SEI thickness as location of XS. But the concept is more general. The key is that we can relate SEI properties such as resistance to the SEI coverage density. The SEI growth is described by its electrochemical reaction. Now, by coupling the dendrite growth and SEI growth on top of the lithium metal dendrite, we can predict battery performance, especially for lithium metal batteries. We analyzed various factors, including current density, SEI resistivity, and SEI local defects to observe how they affect the dendrite growth. The key conclusion is that flat lithium surface, uniform SEI layer, and low SEI resistivity are important to reduce dendrite formation. How to stop dendrite growth? Lithium deposition is inherently unstable because of unavoidable perturbation. See, a small protrusion is formed here. The lithium flux forms a spherical diffusion concentrated toward the tip. Therefore, the tip grows faster and forms a sharp dendrite. This dendrite easily penetrates the separator, called short circuit. Now, our separator generates a shielding effect. When the dendrite pushes our separator, the shielding effect will cause lithium ions to deflect away from the tip, therefore causes the lithium metal to grow flat. Here is a comparison between our approach and a regular separator. On the left is a regular separator. We can observe the dendrite quickly penetrates the separator. Well, for our approach, there is no diameter penetration after 1 hour. We can observe the diameter penetration on the left, and the surface keeps flat for the separator on the right. So here's the conclusion. Battery degradation modeling and health optimization can significantly improve the cycle life. Electrochemical mechanical degradation modeling of lithium-ion batteries provides important insights into the degradation of battery cells in terms of stress, fracture, and delamination. The coupled SEI and the dendrite growth models shows that flat lithium surface, uniform SEI layer, and a low SEI resistivity are important to reduce dendrite formation. Learned sampling and early stopping strategies can significantly accelerate battery parameter estimation. Machine learning integrated with physics is highly valuable for battery design. Thanks. I'm happy to take questions.
Thank you, Professor Liu, and what a fantastic start to this event. That was a truly captivating exploration of cutting-edge methods being used to build better batteries. I'm sure everyone is eager to delve deeper, so let's dive right into our Q&A session. We already have some excellent questions submitted, so I'll jump right in. Battery degradation is a complex issue. You mentioned various mechanisms at play. Which one do you see as the most critical factor in limiting battery lifespan, and how does your research address it?
Thanks for the question. Many factors affect the battery degradation. The specific dominating mechanism will depend on the battery chemistry. I would say for most of the current batteries, the dominating degradation mechanism is the SEI formation. So by looking at the factors that contribute to SEI formation, we can have a good understanding of how the battery degradation will evolve over time. And at the same time, we can develop better technology to reduce SEI formation, therefore improve the battery cycle life. Now, the other important factors will be the loss of active material, such as on the anode side or cathode side. So they will also contribute significantly to battery degradation. And in terms of other mechanisms, such as manganese dissolution, transition metal dissolution, and other factors, they will also contribute to the degradation, especially in the later stage.
Thank you, Professor. Moving on to another question from the audience. Beyond battery design, can your models also be used for optimizing battery management systems?
Yes, that's a very good question. An important task of the battery management system is to understand the state of the battery based on the usage history and provide the guidance for the use for the next time period. So one important area that we are working on is to, based on our comprehensive degradation model, to develop a reduced order model so that it can calculate faster. And for the battery management system, there are several ways that you can implement that. One way is you have a reduced order model which can calculate fast with the onboard hardware. It's calculated inside your vehicle. So this requires to have a simplified model so that the chip can handle that amount of calculation. And with this, we can, for instance, tell what is the state of health of the battery. We can tell what is remaining life, And also, based on the model, there can be a better strategy in terms of control to prolong the battery life. For instance, maybe we want to balance the kind of power requirement. For instance, if there's a demand of sharp acceleration, then maybe the battery management system can work out the better strategy based on the current state of health of the battery to deliver the appropriate uh, power supply so that it does not stress the battery too much and therefore causes quick degradation of the battery.
Yeah, and looking further ahead, do you have a forecast, let's say 5 years from now on, what battery technology and battery energy management systems will be trending?
Yeah, so there are multiple competing technologies being developed to improve the current battery technology. So currently, the dominating battery is lithium-ion battery. Uh, there's primarily like on the anode side, we have graphite-based and some mixed with silicon to enhance the capacity. On the cathode side, there's a NMC material. There's some other materials such as LFP and some other battery chemistries are being developed. Now, talking about the future battery technology, my view is that there will be multiple technologies competing and being developed, and we will see which technology will win in the long term. And for instance, we could look at solid state battery technology. We could look at lithium metal battery, which with the lithium metal as the anode material, it provides the highest theoretical capacity because you don't lose any mass as a hosting material. So I think all these new technologies will evolve in a direction to provide higher energy density, higher power density, and longer cycle life.
That's a great answer. Throughout your presentation, you touched on using machine learning within your research, and our audience are keen to learn about the application of AI in battery design and innovation. Does your research involve any AI-powered tools or automation in the battery development process?
Yes. So when we look at the battery modeling, we have both physics-based battery modeling, and also we use machine learning to help the physics-based battery modeling. The machine learning approach is more data-driven. So you need a lot of data to train a machine learning algorithm, and the machine learning can also be used in different ways. So, for instance, in the examples I have shown, so we use the machine learning to learn the physics-based model. So those data actually are generated by physics-based model, and then we can use machine learning to accelerate the calculation. Therefore, we can explore a larger design space. In terms of specific application, uh, a major challenge in design is the huge parameter space. Using machine learning to learn the entire design space itself is also a challenging task because you need a lot of training data to learn that. So suppose, for instance, you use a finite element calculation to generate this data. And when you generate the data, you already partially solve the problem because you need to generate data for all different parameter combinations. So one strategy we have actually is to use the better part of both physics-based model and machine learning so that they can work together to help with battery design. For instance, we don't need the machine learning or AI to learn the entire battery behavior for all the parameter combinations. We only need the machine learning to learn locally where it's more promising for the combination of the parameters. Therefore, we can dramatically reduce the amount of data requirement. We can also use AI to help estimate battery parameters for the physics-based model, which is another important application area.
Thank you, Professor Liu. Lastly, I'd like to close the Q&A with just one final question. Given your expertise, what are your thoughts on the potential advantages of sodium and lithium FSI in battery technology compared to lithium and lithium PF6, respectively?
For the sodium-ion batteries, there are a lot of study, and many of the study focus on stationary storage, such as for grid applications. I think there's a lot of good works going on in that area. Talking about the electrolyte, so the LiPF6 has been used for a long time. Developing a good electrolyte is a challenging task. So the LiFSI is a new type of electrolyte which offers some advantages comparing to the conventional electrolyte, such as higher ion conductivity. It's more stable electrochemically and thermally. I think the current traditional electrolyte has advantage of lower cost. So with the new electrolyte provide a better performance and with lower cost in the future, we will be able to see that this new type of electrolyte will be used more in future generation batteries.
Thank you so much, Professor Liu, for your insightful answers to these excellent questions. Unfortunately, that is all the time we have left for this session. However, any questions we didn't have time to address will be sent to Professor Liu after the event. And don't forget, just like all the other talks from today, this presentation will be available for on-demand viewing for the next 30 days, allowing you to revisit Professor Liu's valuable insights at your convenience. Once again, a big thank you to Professor Wei Lu, and we'll be back soon with the next talk.
Thank you.